the next unit where we're going to get into systems of equations. This one's going to get deep into some theory, so if that's not what you're into, you may want to skip to some problems or the next video. Unit 5, which is the unit we're moving into, is all about systems. First, let's introduce what systems are, why we need systems. So let me ask you a question. Can one equation describe every situation? Think about that. Does one equation model everything? Well, no, of course not. And I can give you a very simple example. Let us say that two items cost $10. Believe it or not, two items cost $10 is a system of equations. And you probably know the price each item must be by looking at this, and you know that both items need to be $5. But this is actually a system of equations. And I'm going to show you how that works. So let's think about this. And I'm going to show you how that works. But before we go any deeper into that, that's just an example of what we're going to do. But let's understand the concept first. Let's review quickly linear equations. We have y equals 2x plus 1. We know that we can graph this, and we know that this is the y value, this is the slope, this is the x value, and this is the y-intercept. We know that. Now, one thing you may not have explicitly known, but you probably felt, is that these linear equations represent many solutions. Many solutions. And what does that mean? It represents many solutions. Well, that means that there's many x's and y's that can satisfy it. Because as you know, this runs about this line here roughly, and there's all these x's and y's, these different x's that satisfy different y's, and it just goes on and on. So a linear equation represents many solutions. So let's think about, let's just realize that if it represents many solutions, it more or less represents infinitely many solutions because it just goes on and on. So why does this bring us to systems? Well, let me show you. This brings us to needing systems because when we have two linear equations, we find a very interesting property. So we have y equals x plus 1, and we have y, let's make this a different color. Y equals negative x plus 5. Okay, now we find a very interesting property when we make the system of equation, and we're going to be able to find one solution, most of the time, one solution that can satisfy both of these. So think about that. That's the beautiful thing of it. The beautiful thing is we can find one solution for both. One solution for both. Okay, and let's visually represent what that looks like. So we have x plus 1. We're going to have a y-intercept at 1 with a positive slope of 1. So there and there, and over 1, up 1. Okay, and we're going to connect those lines. It's a pretty good line right there. And then let's go to green. Now we're going to have 5. We're going to have a point at 5 and a slope of negative 1. Okay. and over 1, down 1, and we're going to intercept right about there. So let's take a look at this. So X marks the spot. The very center of this, right here, this represents solution to the system. To system. So what does that mean, solution to the system? Well, this point right here, let's define that point. The point, we'll mark it, the point 2 and 3. Point 2 and 3. This defines the solution to the system. So both of these can be solved with 2 and 3. Okay? So let's erase this and let's consider that a bit more. What does that mean? When we say we found a solution for a system, and just realize the beauty of this, we're saying we found the ordered pair, the x and the y, that satisfies not one, but 2 equations. So let's look at this. Let's start with this top one up here. So we're going to take this value and we're going to plug it over here. 3 equals the x value, 2 plus 1. Okay, that's true for this one. Now let's go to the green one here, and we're going to say 3 equals -2 plus 5. Okay, you'll notice that both of these are true. This is 3 equals 3, and this is 3 equals 3. So when we found that ordered pair, we found a solution to a system. Now, this will apply across very real situations, which I'm going to get into shortly. But this idea, this visual representation here, this numerical representation, it applies across this wide range of ideas where you know a certain couple details, but you don't know the other. You can just use this universal law to find those answers. So let's explicitly define what a solution to a system looks like. Let's explicitly define this. It is an x and a y that satisfies 2 or more equations. And let's keep it 2. Satisfies, spelling don't count, satisfies 2 equations. An x and a y that satisfy 2 equations, like our example here. Let's move into a real world application. I'm going to go ahead and erase everything and pop a problem up there for you. So here is the big powerful theme of the systems of equations. This is the information we're given. A movie theater sells tickets. Adult tickets cost 10. Student tickets cost 6. 10 total tickets were sold. $86 was collected. So I'm sure that if this is your first time seeing this, and this is the information you're given, you have no idea how to take this information and solve, let's say, well, actually, you would be given part of this information and asked to solve problems. But when you're given this information now, you would have no idea, how do I set this up? What does this mean? What is the purpose of this? How do I graph it? So let's do that. What you need to do is realize that you need to define your variables, and you need to realize that A is going to be your adult tickets, and it's going to equal 10. We'll drop the dollar sign. S is going to be your student tickets, and it's going to be 6. Okay. Now you also must realize that if you added the A tickets and the S tickets, you added A. Well, actually, that's not true. If you added, let's say, let's define it as. So, okay, let's define it as rather. Um, let's actually define the variables differently. Let's say that rather. Let's say it this way. We know that A plus S equals 10 because we have 10 tickets sold. And A is the number of adult tickets sold, S is the number of student tickets sold. And let's also define the second portion as, let's say, 10A, because we have $10 per adult ticket plus, and let's clear that out, 10A plus 6S, because we have $6 per student ticket, equals 86. Okay, there we are. See, this is the information you have here. So with this information, you can solve how many adult tickets were sold and how many student tickets were sold. And I'm not gonna get into how to do that. We are in this unit, but I'm not gonna get into it yet. But this is the kind of problems you can solve using this. Now, just to talk just finally on what we're going to learn in this unit 5, is we're going to learn a few things. Really, it's going to be 4 key ideas surrounding systems of equations. Graphing systems, using substitution to solve systems, using elimination to solve systems, and how to solve word problems dealing with systems of equations. And remember, the key idea with systems is finding values that work for all the equations presented. So what I'm going to do now is I'm going to clear the board out, and I'm going to provide you with, well, we're going to work through 4 example problems together. I'll show them to you, you do them, think about them, and then I'll think about them out loud with you. Let me clear the board. So we're given a question here. We're asked to explain in words why this situation needs 2 equations, not 1. We're given the total number of coins, which is 12, and we're given the total value, which is $1.02. Go ahead, take a moment, think about this situation. Why does it necessitate 2 equations? Well, this is how I perceive, or how I will explain why we need 2 equations here, not 1. So we're given the total number of coins and we're given the total value of coins. Well, the reason we have to use 2 equations is because there is a limited, there's a number of ways that coins could be combined to make different amounts. But if we know the total amount, there's only one way the coins can be combined to make the amount 1.02 or $1.02. So we would approach this problem knowing, and I'll just keep it in words. We would know that there's only so many combinations of coins, and I'm assuming this is U.S. value. I'm not going to go into the equation, but that's kind of the reasoning behind it. Let's move on to a second problem. Sorry to combine learning with asking questions, but I introduced this symbol here. This symbol means that these 2 equations are part of a system. Now, with this system here, 2 linear equations, I'm going to ask you, what does a solution represent? Well, I'm sure you had a great answer. Whatever it was, this is very conceptual learning, so regardless of what it was a good answer. But let me explain what a solution represents in this scenario. The solution, when you have a system of equations, represents what x and y value can satisfy both equations. And you'll notice that there's different parts of the equations interplaying. So we have to find an x and a y that satisfies y equals 2x plus 1 and y equals negative x plus 4. And there's only going to be typically one equation of x and y, one x and y that works. Okay, so that's my answer to that question. Let's move on to a true or false question. So here's a true or false question, and the question I'm asking is a system of equations can have only one solution. Is that true or false? Well, this one may have been a little tricky for you. It's a concept I haven't introduced, but I'd love to hear what you answered if you weren't familiar with this before. The answer is false. You may have noticed I alluded to generally, typically, system of equations has one solution. There are exceptions to that, which we'll get into in later videos. Let me give one final question. I will not erase the board this time. The final question is going to be I would like you to describe a situation where one equation is not enough. Go ahead, give that a shot, and then I will do one myself. So I hope you came to a nice example. Again, feel free to leave it in the comments if you'd like. My example for when we would need a system of equations is, let's take the situation where we have bank accounts with different interest rates and different amounts invested. We would need to have a system of equations to determine either one, how much we would return, or two, how much we could return based on different amounts invested. So that's my example. Look forward to getting into some problems that are more hands-on and walking through problems. But thank you for watching the video. If you found something useful, please like, comment, or subscribe, and I'll see you in the next one.